Okay, welcome to this particular lecture is section 2.1. We're going to be looking at atoms, ions, molecules, compounds, and various other things, including the periodic table. So go ahead and get your spiral out and take notes over this. Again, you can pause any time that you feel you need to take a look at the slide or any diagrams. Okay, the first term we're going to look at is biochemistry. Bio means living or life, so studying biochemistry is the chemistry of living organisms. Now, I'm not going to ask you any questions about this diagram. I just wanted to point out how important biochemistry is. So you can see, just looking at the research aspect, that anywhere from determining cure for cancer, livestock health, etc. So I'm not going to ask questions, but if you want to just take a look at this, that would be fine. Okay, so atoms are made up of, and you may have had this in a previous class in elementary school, but atoms are made up of subatomic particles, electrons, protons, and neutrons. Make sure you know where they're located, the charge, and the symbol for them. So electrons, symbol here is a yellow. Okay, these are energy levels, so they're surrounding the nucleus. They have a negative charge. Protons, positive charge found in the nucleus, and neutrons, a neutral charge. That's what this N with a superscript 0 is. Okay, that means no charge. So the number of protons and electrons, when they are equal in number, which means if I have a -2 and a +2, then it is a neutral atom. So they have to equal each other in the number of protons and electrons. On the periodic table, I'm not going to read all of this to you, so you can pause. I just want to point out that every periodic table is a little bit different, so make sure you try to find the key. Sometimes the atomic number is on the bottom, and sometimes the atomic mass is in the upper corner. The atomic number will tell you 3 different pieces of information: the number of electrons, protons, and the atomic number. The atomic mass will give you in units, and usually it's a decimal. It could go out further to the hundredth, thousandth, etc. Okay, so just make sure you know what these numbers mean. Okay, this might be a good slide to pause on also. So on this, the mass number, you're going to look at the periodic table. So here is sodium, and 23 is the mass number. They labeled it for you. But if they don't give it to you, you can always look at, sometimes they'll write it like O-12 or something, or Na-23. So that means that the mass number is 23. When you're looking inside the nucleus, okay, here you have the protons, the electrons are on the outer energy level, neutrons. Now, the periodic table will not give you the number of neutrons, but you can figure that out by subtracting mass number and mass number and protons will give you the neutrons. So here, the example, 23 is the mass number, 11 protons. That will never change for each element. That's the identity. Okay, that's what this message, or what it says up here. So when I subtract the 2, I will be left with 12 neutrons. So an element, I've been referring to that on the periodic table, is made up of only one kind of atom, and so therefore it is pure. Now again, you do not need to write all of this down. Maybe just pause it and just read over it. It talks about different kinds of elements. Some are found in nature, some are synthetic, some are just recently discovered. But at least know the definition, and it is pure. Isotopes. Now I kind of threw out that something like Na-23. So here are 3 types of carbon. They vary slightly because of the mass number and the number of neutrons. So they are isotopes. So they have a variation of the atom that have either gained or lost neutrons. Now don't just look at gained or lost if you have a test quiz question, because there's another definition, an ion, that gains or loses electrons. So make sure you pay attention to that. So they all have the same atomic number. Remember, the protons is the fingerprint of the element, so that will never ever change. You'll notice protons, 6 for all of them. And the neutrons do change. So here's 6 neutrons. This is the one you'll find on the periodic table. So I could have carbon-12. Carbon-13 is an isotope with 7 neutrons. And carbon-14, you may have heard, they use that for carbon dating to determine the age of a fossil. So if you change the number of neutrons, you are changing the mass number. Okay, so just know the definition of an isotope. A compound is when you have a substance made of two or more different kinds of atoms. So here's an example. Here's table salt. I've got one sodium, one chlorine, so it makes sodium chloride. I have one carbon, which is the black, and there are 4 hydrogens. Water, 2 hydrogens, and 1 oxygen. So there are at least two different kinds of atoms bound together that make a compound. Now this one, if you're reading in the book after you take these video notes, or if you did it the other way around, you will find that they list a lot more elements. These are the elements I want you to know because we are only focusing on the macromolecules. So if you read this statement carefully compared to the one in the online textbook, you'll see the difference. Percentages, I've seen sources that 95, 98, even up to 99. I'm not concerned about the percentage, but I do want you to know the 6 elements found in all living things. And so they are found in the 4 macromolecules that we're going to cover in a later lecture. And those 4 are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And I use a little mnemonic device called NCHOPS. So I took the symbol of each, so nitrogen, carbon, hydrogen, oxygen, phosphorus, and sulfur. Now here's one that sometimes kind of messes up students a little bit, if you want to say that. S stands for sodium, but the chemical symbol for sodium is Na, not S. So just be careful about that. Okay, on this particular chart, I'm not going to ask any questions. I'm not going to ask you to re-diagram it. I just wanted to put it into perspective on how mixtures and elements and compounds, pure substance, okay, these would be atoms, so how everything kind of relates together on the hierarchy. And again, you can just pause it and just take a look at it, but you don't need to put this in your notes. Okay, an ion. Now we talked about an isotope that has a different number of neutrons. Now an ion is an atom or a group of atoms that has a positive or negative charge, and it does that by gaining or losing electrons. So if I take sodium and it has a plus beside it, that's a good indicator that it's an ion. It has some kind of charge. Well, 11 protons, that will never change. It will always be 11 for sodium. But if it has 10 electrons rather than 11, 11 would make it a neutral. 10 electrons gives it a +1 charge. If I add those two together, plus 11, negative 10, I get +1. So that means it has a positive charge, and it is an ion. So you can either write it with a plus sign or a +1. That does not matter. So a positive ion means there's more protons than electrons. So here's an example. When there are 2 or more, you write a +2 behind it. Okay. A negative ion, more electrons than protons. So this one has a negative charge because there's more electrons. Chemical bonds. Chemical bond can be attracting, sharing, transferring, and it's always with the outermost electrons, never the ones that's closest to the nucleus. Okay, those kind of keep it stable. If there's only one electron, then the only option it has is to share like hydrogen does. Okay, so 3 types of bonds. There'll be several questions about this. So the 3 are ionic, covalent, and hydrogen. We're going to, in this unit, focus on ionic and covalent. We'll mention some about hydrogen because we'll look at that in the water molecule, but the water molecule also can have covalent. So let's start with ionic. So this is when you transfer electrons. So you're going to give an electron to another atom. Okay? So as you're looking at this diagram, this animation, the sodium has 1 electron, the yellow one, in the outer energy level. They're not diagramming the other electrons. The chlorine has 7 in the outer energy level. Well, to make it happy, so to speak, it likes having 8 in the outer energy levels. It's easier for the sodium to give or transfer that 1 electron to the 1 chlorine, and it makes sodium chloride. Okay, so that's transfer or ionic. Okay, covalent. Now, this one's kind of subdivided into polar and nonpolar. So a polar molecule has poles. So it's like a battery, a positive and a negative charge. but the electrons are not shared equally. So it's like a tug of war where the larger element, atom, has more strength, and so it's pulling the other to one side. So it's a little lopsided. There's a heavier pull on one side. So looking down here, so if it's hydrophilic, that means it's water loving. Philic is loving. So that means it's attracting, it's sticking to it. So it's putting magnets together, okay, or battery, whatever you want to say on that point. Okay, the other one is nonpolar. So here the electrons are shared equally. It's an equal, there's no movement in the tug of war, it's a tie. And this one has no poles. Okay, there's no battery, no magnet involved. This one is hydro means water, phobic. So like when you have a phobia, you're afraid of something. So this is a fear of water. So this would be oil and water do not mix. Okay, so that would be an example of something that's hydrophobic. So that's covalent. So they're sharing electrons. Ionic is transfer. It's giving up its ions. I'm not going to read through this. You can pause and just kind of glance over it. It's a lot that I've already said. Just a little bit different diagram. This one actually has the arrows showing the direction of the pull. Excuse me. So in this case, this is H2O. The oxygen has more power behind it, so to speak, and it's pulling and holding on to the two hydrogens. Okay, I wanted to include this diagram because it has single lines, double lines, triple lines. And so what do all those mean? Well, those are the bonds. So every line is two electrons that are bonded together that are sharing. So if I have a double bond, that means I have a total of 4 electrons that are hooked together. Okay, so these are just some examples on how they are, the structural formula is written. You might want to jot those down in your notes. Okay, nonpolar, again, no poles, but it's still sharing, but now it's equally. So here I can see this is carbon dioxide, CO2. So here is one that's being shared, a pair, so I could put one line in between it to represent 2 electrons. Okay, on this I kind of found a diagram to put all of them together on one page so you can kind of compare and contrast. Now here's a new little symbol. Okay, this is a lowercase delta, and that lowercase letter means partial. So it is a partial charge, a partial positive charge, say that fast 3 times, and this is the negative charge. Okay, so that's a covalent bond on that. So that's sharing, but one has a slightly more of a charge than the other. Okay, and the third is a hydrogen bond. Now we're going to see that in our next lecture when we're talking about the properties of water. I'll refer to this again, but here's the water molecule. So the 2 yellow would be your hydrogen, this is your oxygen, and so in between each hydrogen and one oxygen it comes together and it forms a hydrogen bond. That's what holds the water molecules together to make a water droplet. We're also later going to see that a hydrogen bond will hold the DNA molecule together, and these are bases. Again, we're going to write this down later, so you don't need to worry about it right now. Okay, of the 3 bonds, the hydrogen bond is the weakest of the 3. The reason why, especially in DNA, it needs to be able to break apart to open up in order to replicate itself. Okay, a molecule. A molecule is when you have 2 or more atoms held together by covalent bonds. So most of these are found in organisms, plants, animals, etc. They are molecules, and some even occur naturally, like water and oxygen gas. Okay? Okay, now if you have 2 of the same atom, exactly the same, that is called diatomic. Di means 2, 2 atoms. So here are the examples of the common diatomic molecules that exist. These are all gases. Okay, on the periodic table, just refer to the purple ones to show you where they're located. Okay, so you can always recognize this more likely would be a gas on all of these. Okay, so that kind of wraps up our video lecture. So what you need to do is definitely look over it before our exam or quiz, whichever we have, or both. And then go to the online textbook, go to section 2.1. Either you can go online and take notes, or if you want to print it, if you like having a hard copy, it's up to you. read and add anything that I did not cover in the lecture, but do not write exactly what I said in the lecture down. I do cover a lot of the same information. Maybe you can just highlight anything that's found in both the video lecture and the notes. But do take notes, look at all the figures, and jot that down in your spiral. So until next time, I will talk to you later.